This lecture is part of an online course of multivariable calculus, and I'm going to talk about surface integrals. So let me start by a surface S to be a surface in R3, and I'm going to take f as a function of x, y, and z that is defined on the surface S. F is basically a function that is defined on the surface S, and it goes to R. Okay, then the surface integral, or basically the integral of f ds over the surface. So we call it surface integral because it's integral over a surface. It's basically this notation that we are going to use for it. It's integration with respect to surface area. The ds that I have in here, it's the element for surface area. Okay, so now how to compute that? Well, as usual for calculating line integrals, basically integral over curves or integral over a surface, we need to parameterize the surface S. I talked about parameterization in previous videos, and to do that, for parameterizing a surface S, we need two parameters, and I'm gonna write R of u and v. I'm gonna use the parameterization with two parameters u and v, where basically u and v, they live in a domain D that is a subset of R2. So it's in UV plane. Okay, so let me explain what we have. This is x-axis, y-axis, and then z-axis. Let me basically move everything a little bit so that I have more space to write. I'm gonna move this one side, that side. Okay, so I have a surface S, something like, for example, this surface S, and I'm gonna use two parameters to parameterize that, and the parameters would live in UV plane. So this is U axis, this is V axis, and I have a domain D, and then from D I can use the parameterization R of U and V to go to S. Okay, so that's why we need to have two parameters. It's just because we have a surface S and we have 2 degrees of freedom. If we had a curve, if you remember parameterizing a curve, we just have one parameter, but now we have 2 parameters. Okay, then what we're gonna do, as usual, we're gonna plug in our parameterization into the integrand, and then after we do all of that, we say that the double integral of f ds over the surface S is what? I'm gonna take basically a sample point and the little areas that I have in here, I'm gonna partition S into small parts. Let me have a better graphing for it. So I just have a small parts. I'm gonna call this delta Si. So this is just a little part of the surface area of S. Then I'm gonna choose a sample point like this, xi, yi, and then zi. I'm gonna find f at this sample point, and then I'm gonna multiply it by delta Si. I'm gonna sum over all of them, all of these little parts times f, and then I'm gonna take the limit just to make sure that these little areas are very small. Okay, that's what we define it. But what is delta Si? Okay, delta Si, I need to be a little careful for that. So I'm gonna zoom in this little part of the surface area. I'm gonna zoom in and I'm gonna graph it like this. Okay, so this is delta Si. Okay, at this point we have R of U and V, and then I'm gonna move to this point, and on this point just assume that, actually let me graph it better. So we have R of U, so we just change U a little bit, delta U, and V is fixed. And if we go to this point in here, I have this vector, and on this point we just fix U and then change V a little bit, delta V. Okay, so I'm gonna call this vector the vector A, I'm gonna call this vector the vector B, and if you remember, delta Si is approximately it's a parallelogram with sides A and B. Okay, and the area of the parallelogram is what? Let me write A and B first. So A is approximately, so if we just move from R of U V to R of U plus delta U and V, it would be partial derivative of R with respect to U delta U, and then B, the side B in here, it's just because we have U and V, and then we go to U and V plus delta V, so U is fixed. We just change a little bit in the direction of V. We have partial derivative of R with respect to V delta V. And the area of the parallelogram is the length of the cross product. Is the length of the cross product of A and B, okay, which is what? Which is approximately R with respect to U. I use the other notation for this, which is R with respect to U cross product with R with respect to V, and then delta U and delta V would be basically some constant that I can take them out. Okay, so now I calculated the area of this little part in here on the surface S, and then I'm gonna take the limit. So when I take the limit, I have ds, which is the length of R of U cross product with R of V, and then du dv. Perfect, I calculated ds. So now if we want to just write everything that I want together, the surface area, the surface integral of f of x, y, and z ds over the surface S is equal to the double integral of f of what? I'm going to parameterize S with parameters u and v. I'm going to plug in the parameterization into the integrand, and then I'm going to take the integral over the region D, where is the domain for my parameterization, and then I'm going to multiply it by ds, which is r with respect to u, r with respect to v, the cross product of these two, and then the length of it. Because I have a function in here, I need to have a function in here. I don't want to have a vector in here. And then du dv. Perfect. This is the integral over the surface S, or basically we call it surface integral. Okay, I'm gonna give you the application of it, the integral of a vector field over a surface S, but I'm gonna justify it later in the other videos. I just want to put them together, that's why. So the double integral of a vector field, the ds over the surface S, it's equal to what? It's equal to the double integral. I'm gonna parameterize the surface S with R of u and v, and then I'm gonna take the double integral over the region that is the domain of my parameterization. I'm gonna do the dot product with Ru, Rv, du, dv. You see the difference, right? I have a function in here. That's why I put the length of the cross product in here. I have a vector field in here, so basically I have a vector in here. That's why I need a vector in here, and I'm not gonna put the length of the cross product in here. I'm just gonna put the cross product in here. Okay, this is the double integral of a vector field over the surface S. We're gonna talk about this later, but this is basically the flux of the vector field F through S. And the flux is basically the flow of the energy. And if I want to be more specific, the vector field F is a vector field defined on S. Okay, let me just give you a recall of the previous videos that the double integral of 1 ds over the surface S, okay, instead of a function, I just have 1 in here. It gives me the surface area of S. Okay, we talked about that in previous videos. Great. Let me go over one example in here. So let's look at this example. The double integral of y ds over S, where S is the portion of the cylinder, x squared plus y squared equals to 4, that lies between z equals to 0 and z equals to 5. Okay, let me show it to you, the graph. This is the cylinder, okay, and equation of it is x squared plus y squared equals to 4, and I want the part of it that is between z equals to 0 and z equals to 5. Where is z equals to 5? There you go, it's here. Okay, so we are just want to find the double integral of y over just this part of the cylinder between these two planes. Okay, so I'm gonna start the solution. The first thing that we need to do is to parameterize S. Okay, for a cylinder, the parameterization would be, since z is free in here, I have one parameter as z, and the other parameter would be theta, because the radius is fixed. The radius is 2, so 2 cosine theta and 2 sine theta. This is the parameterization with respect to theta and z. Okay, what is the domain? Theta is between 0 and 2 pi, and z is between 0 and 5. It's given 0 and 5. Okay, so I found the parameterization. Let's find the S. So R of theta cross product with R of z. Okay, what is that? I, j, and k. I need to find determinant of this matrix. And the second row, I'm gonna put r with respect to theta. Let's find partial derivative of r with respect to theta. It would be negative 2 sine theta, 2 cosine theta, and 0. Now partial derivative of r with respect to z. No z in here, no z on the second coordinate, and just one z in here. Okay, so let's calculate that. The first, I'm gonna remove the first row and the first column. So I have 2 cosine theta, and then negative sign. I'm gonna remove first row and second column. It would be 2 sine theta, and then the third one would be just 0. Okay, so what is the length of it? Because I have a function in here, I just need the length of this vector. R with respect to z, it would be square root of 2 cosine theta squared plus 2 sine theta squared plus 0 squared. Okay, I'm gonna factor out the 4, and then I get cosine squared theta plus sine squared theta, which would be just 1 square root, so that's why I just get a 2. Now the double integral of y ds over the surface S, you see everything here is capital S because it's the element of the surface area. Okay, we also had small s before. That was for the arc length in the curve integrals, just as I recall. So I'm gonna put my parameterization into my function. So y is just 2 sine theta. Okay, and then the length of this vector is just 2 dz d theta. Okay, and then z is from 0 to 5, theta is from 0 to 2 pi. Let's calculate that. I have a 4 from 0 to 2 pi. I don't have any z in here. Sine theta would be constant with respect to z, so z is from 0 to 5 d theta. So I get a 5 times a 4, it's 20. The integral of sine theta would be negative cosine theta from 0 to 2 pi. So it would be negative 20, and then 1 minus 1, which is 0. That's the answer for this integral.